This conference will now be recorded.
That is, we have seen in the last class the Shannon's source coding theorem, Shannon's channel coding theorem, and later the channel capacity theorem. And according to that Shannon-Hartley theorem or that channel capacity theorem, uh, the channel capacity is given by C is equal to B log 1 plus S by N, where C represents the channel capacity, B is the bandwidth, and S is the signal power, and N is the noise power. And uh, and we have seen what happens uh, when the in a noiseless channel. What is the condition? That is that capacity is infinity, and for a infinite bandwidth channel, uh, seen that there is an upper limit, and that equation, it is equal to that infinity channel capacity for an infinite bandwidth channel is equal to 1.44 s by n 0. That is in this channel capacity expression, that signal power is, when the signal power is fixed and the white Gaussian noise is present, the channel capacity approaches an upper limit with increase in bandwidth. It is as it approaches infinity, the channel capacity does not become infinity. There is an upper limit, and that upper limit is given as 1.44 divided by s by n0. Okay, we can derive that expression, that upper limit for an infinite bandwidth channel. We can derive this expression, C infinity is equal to 1.44 s by n0. That is, here for convenience I have taken the snapshot from the textbook other than typing. That is, here the noise power, we know that noise power n equal to n0 into b, and initially we are substituting that n equal to n0b in the expression for that channel capacity. That is, C is equal to b log 1 plus s by n, that is the expression. Substitute n equal to n0 into b. Okay, you can note this derivation, that is channel capacity expression, then n equal to that noise power equal to n0 into b, and substitute that n equal to n0b in the expression for the channel capacity. Okay, then next only just rearranging and finding the limit with that b tends to infinity. This here we have b log 1 plus s by n0b, then we multiply the expression by s by n0 and n0 by s. It is here s n0 by n0 s. We are multiplying that above expression. It is the same, s by n0 into n0 by s, b log 1 plus s by n0 into b. Then here we are considering these terms as together, n0 into b by s. Before we can rewrite the expression as s by n0 into log 1 plus s by n0 b raised to n0b by s. This term n0b by s as taken as exponent of this expression, s by n0 into log 1 plus s by n0b raised to n0b by s. And again s by n0, the same s by n0 log 1 plus s by n0 by, we written that n0b by s as 1 by s by n0b. Okay, that n0b by s as it is written as 1 by s by n0b. Okay, That is, we have rearranged the above equation like this. And next we can consider, let us apply the limits as b tends to infinity. That is, our aim is to find the uh, channel capacity when the bandwidth approaches infinity. What is the max that capacity, channel capacity of the channel when bandwidth become infinite, for a infinite bandwidth channel? It is apply the limits as b tends to infinity. For that, c infinity represent the channel capacity when the bandwidth approaches infinity. Okay, then c infinity equal to, we can write as limit b tends to infinity c, that expression for rewriting limit b tends to infinity s by n0, the same expression here, s by n0 log to the base 2 1 plus s by n0 b raised to 1 by s by n0 b. This we have applied that limit b tends to infinity. Okay, hope that you have written that much. Then in the equation, put x equal to s by n0b. That is, we are replacing that s by n0b term as x. This, in this expression, this s by n0b we are replacing by x. Therefore, we can write as 1 plus x raised to 1 by x. This expression becomes that like that. It is, anyway, we are substituting s by n0b with x. Then here, as b tends to infinity, we can see that x tends to 0. Here in this expression we are substituting x equal to s by n0b. Therefore, as b tends to infinity, in this expression x tends to 0. Okay, therefore we can write the above expression as c infinity is equal to, that is, by substituting that s by n0b by x, c infinity is equal to s by n0 limit x tends to x equal to 0, x tends to 0, log to the base to 1 plus x by x raised to 1 by x. That is, that change limit also changed. This, as b tends to infinity, x tends to 0. Therefore, here limit x tends to 0, log 1 plus x by 1 plus x raised to 1 by x. Okay, next we can use the standard relation x tends to 0, 1 plus x by x raised to 1 by x equal to e. Then the above equation becomes c infinity is equal to s by n0. Here s by n0, this expression becomes log 2 e, logarithm of e to the base 2. Okay, that is, that capacity of the channel with the infinite bandwidth equal to s by n0, s by n0 log e to the base 2. Then here by using that logarithm to the base 10, we can rewrite, or in some calculator you can directly calculate this value, logarithm e to the base 2. In some cases only that logarithm 10 will be there. Then you can use this equation, s by n0 equal to log 10 e, that is, taking the logarithm of e to the base 10, then log 2 to the base 10, dividing by that, we get the exact value, and it is equal to 1.44 s by n0. Therefore, that is the expression we have already seen. It is that infinite bandwidth channel, that is, a channel with bandwidth infinity. It has a limited capacity. There is a maximum limit. It has, its capacity is not infinity. It has a maximum limit, and that is equal to 1.44 s by n0. That is about the derivation of that particular expression, that is capacity, channel capacity of a channel with infinite bandwidth.
This conference will now be recorded.
Next is some other parameters regarding this channel, and it is rate to bandwidth ratio, and SNR, and EB by N0 trade-off. It is let the system is transmitting at the rate RB. It is that RB represent a system transmitting at the rate RB, that RB bits per second. And here take that this rate at which the system is transmitting is equal to the channel capacity C. Okay, that is that RB, that rate of transmitting the information, that is that how much bits per second, it is equal to the channel capacity C. Then the average transmitted signal power will be, it is here S represent the average signal power transmitted, it is equal to EB into C. Here EB is the transmitted energy per bit. This here C represent the channel capacity, and here said that the system is transmitting at the rate that channel capacity, that is RB, that is RB is same as that C, the channel capacity. Therefore if EB is the transmitted energy per bit, that per bit the energy transmitting is EB, then that EB into C gives a signal power. The channel capacity is bits per second. Then we have the expression, the channel capacity for the continuous channel C is equal to B log 1 plus S by N. Okay, here S is the signal power, that is equal to EB into C, and note that term EB is the transmitted energy per bit. Transmitted energy per bit. Okay, then here we have that signal power equal to EB into C, and the noise power we have N equal to N0 into B. Then here in the first line we have substituted that S equal to EB into C, and N equal to N0 into B. Okay, S equal to EB into C, where EB is the energy per bit. For that EB into C gives the total signal power, and we have that noise power N0 into B, that from that noise power spectral density, that we have that N equal to N0 into B. Sometimes it is represented as eta. You may be studied in digital communication. Anyway, we have N equal to N0 into B. Then taking this B to the LHS, C by B is equal to log to the base 2 1 plus EB by N0 C by B. Then that C by B is equal to it is converted taking as the logarithm to the base E. Therefore log E of that term 1 plus EB by N0 C by B divided by log 2 to the base E. This we have converted that logarithm to the base 2 to logarithm to the base E. For only thing we will have to do is take logarithm to the base E of that particular term, divide that term by logarithm of that base. Here it is 2 already, for log 2 to the base E. Then just rearranging the terms, only that much. C by B is equal to log E, that is C by B, that log E2 is equal to logarithm of 1 plus EB by N0 C by B. Then here logarithm of 2 raised to c by b is equal to, the RHS is same. All of you please write these terms, this derivation log. Anyway, I will be sharing this particular PPT, and this the recordings of these sessions will be sharing. Anyway, all of you please note down all these. Okay, log 2 raised to c by b is equal to log e1 plus eb by n0 c by b. Just rearranging the terms. Then here LHS and RHS, both terms are logarithm of a term to the base e. Here also logarithm of a term to the base e. Therefore, we can write as that avoiding that logarithm, 2 raised to c by b is equal to 1 plus eb by n0 c by b. From this eb by n0 we can write as, that is this one goes towards LHS, that gives 2 raised to c by b minus 1 equal to eb by n0 into c by b. From that, eb by n0 is equal to 2 raised to c by b minus 1 divided by c by b. Okay, 2 raised to c by b minus 1 is divided by c by b. Then in this equation, I think you are visible to this slide, and you have that zoom option there. You can zoom for better viewing. In this equation, eb by n0 is the energy per bit, that is this eb is the energy per bit to noise spectral density ratio. In this term, in this expression eb by n0, we can say energy per bit to noise spectral density ratio, and c by b is called the bandwidth efficiency. C by b, this expression here, c by b is termed as bandwidth efficiency. Okay, all of you please note the terms. eb by n0, we can say it is the energy per bit to noise spectral density ratio, and c by b is called the bandwidth efficiency. C by b is the bandwidth efficiency. And when c equal to rb, this expression we have c, and rb we have seen that rb is the rate at which that system is transmitting. When that channel capacity and the rate at which the system is transmitting is same, then that is c is equal to rb. Then substituting that in the above equation, we can rewrite the expression eb by n0 is equal to 2 raised to rb by b minus 1 divided by rb by b. And here rb by b is called the rate bandwidth. This term rb by b, rb is the rate at which the system is transmitting, and b is the channel bandwidth. Then here this rb by b is called, this parameter rb by b is called the rate bandwidth. And we can see the trade-off between this rate bandwidth ratio, that rate bandwidth to the signal to noise ratio. In the next slide we will see that. Okay, here rate bandwidth, that is rb by b, is plotted versus that signal to noise ratio rb by b, that rate rb by b, rb by b, that rate bandwidth versus signal to noise ratio is plotted. And in this plot, we can see the plot is separated into two regions. This one is shaded here and the unshaded portion. And for RB less than C, here and in this plot, that is that RB by B versus signal to noise ratio, that is here that EB by N0 in dB actually we are plotting. Here this line represent which corresponds to that RB equal to C, the capacity boundary, just RB equal to C, and the region below this graph, that is corresponding to that RB equal to C, it represents RB less than C, and above that RB greater than C. And here the significance of this plot is that we can say for RB less than C, error free transmission is possible. That is, in this region, it represents the region corresponding to where the error free transmission is possible. Error free transmission is possible. And similarly, region above RB, region corresponding to this RB greater than C, is in that expression, if we take the different condition RB equal to C, then we get this particular plot. If we plot that RB corresponding to RB equal to C, then region above and below RB less than C, this region we can say error free transmission is possible, and RB greater than C, the error free transmission is not possible. Then we can see some more cases, that is this what is meant by this Shannon's limit. That is, we have already seen that for infinite bandwidth, the channel capacity C infinity equal to, we know that 1.44 S by N0. Okay, then the channel capacity of an infinity channel 1.44 S by N0. Here this S equal to EB into C, that EB, the energy per bit, and the C channel capacity. And for this particular case, that is where C infinity, we can substitute that C infinity for C. Therefore, we can write that S equal to EB into C infinity. That is rewritten here. C infinity equal to 1.44 EB C infinity by N0. From this EB by N0, we get 1 by 1.44, 0.693. That value we get EB by N0. That is that we know that EB by N0 is the energy per bit to noise spectral density ratio. That is, we have already seen that in that expression, EB by N0. Then that is equal to, in this case, that is for a infinite bandwidth channel, that C infinity, by substituting that C infinity, we get that EB by N0 is equal to 1 by 1.44 equal to 0.693. And if we take this EB by N0 value in decibel, 10 log that EB by N0, that give 10 log 0.693 minus 1.6 dB. Thus EB by N0 equal to minus 1.6 dB for B tends to infinity, corresponding to that channel with the bandwidth tends to infinity, that EB by N0 is minus 1.6 dB. That is shown here. That is, here we have plotted that rate bandwidth RB by B versus EB by N0 in dB. Therefore, here minus 1.6 dB will be here, and it corresponds to that channel bandwidth equal to infinity. Okay, and this particular value is termed as Shannon's limit. That is, EB by N0 is equal to minus 1.6 dB for B tends to infinity. This value of EB by N0 is called Shannon's limit. It is shown in the figure, and the capacity at Shannon's limit is that is, we can say at that Shannon's limit, that is minus 1.6 dB, that is the Shannon's limit. At that limit, the capacity of the channel is equal to 1.44 S by N0. The capacity of the channel equal to 1.44 S by N0. Okay. Therefore, that's about that rate bandwidth versus signal to noise ratio diagram.